So, hi everyone, I am Mohammad Gazan and Boriongan from Group 5, and today we're gonna discuss electron configuration. So, basically, electron configuration of an atom is the representation of the arrangement of electrons distributed among the orbital shells and subshells. Commonly, the electron configuration is used to describe the orbitals of an atom in its ground state. What we mean by ground state is this electron should be at the least energy level, but it can also be used to represent an atom that has ionized into a cation or an ion. Cation is a positively charged ion, while an ion is a negatively charged ion. So by compensating with the loss of or gain of electrons in their subsequent orbitals, many of the physical and chemical properties of elements can be correlated to the unique electron configurations. So the things that can definitely determine the factor for the unique chemistry of the elements are valence electrons and the electrons in the outermost shell. So energy levels, also called as electron shells, are fixed distances from the nucleus of an atom where electrons may be found. Electrons are tiny negatively charged particles in an atom that move around the positive nucleus at the center. On that note, electrons altogether can create a negative charge that balances the positive charge of the protons in the atomic nucleus. Electrons are extremely small to the point that the mass of electron is estimated as 1,000 times smaller than the mass of a proton, and we need to take into account that the number of electrons is equal to the number of protons if there is no charge. So in this picture, we can see that there are two electrons in the orbital. So this is the diagram of a helium. So basically, helium has electronic configuration of 1:2. Sorry for that background. So next is this periodic table can illustrate the blocks of each group or each part of a periodic table. We can see the blue one as the P block, while green one as we can see the blue one as the S block, green for the P block, orange for the D block, and lastly pink for the F block. So in summary, this table tells us that the subshell SPDF respectively contains of 2 maximum electrons for S, 6 for P, 10 for D block, and lastly 14 for F block. And in every shell, there will always be S block, S subshell, second and higher for P, third and higher for D, fourth and higher for F. And the name of this subshell is S for sharp, P for principal, D for diffuse, and F for fundamental. So that's all for this first part of our report. So thank you guys.
Assalamualaikum. I am going to discuss the Aufbau principle. The Aufbau principle, meaning building up from the German word Aufbau, is used to determine the electronic configuration of an atom or ion. It states that the maximum of 2 electrons are put into orbitals in the order of increasing orbital energy. The lowest energy orbitals are filled before electrons are placed in higher energy orbitals. And according to the Aufbau principle, means that electrons fill lower energy orbitals first. You can see here the energies of the atomic orbital, starting with the lowest energy, and that is the 1s atomic orbital. Then we have the 2s atomic orbital, then the 2p, which are degenerate orbitals, which means they all have the same energy. Then the 3s orbital, and then 3p orbitals, which are degenerate, and then the 4s orbital, which is lower energy, then the 3d orbitals. On the right here, we have the order of filling of the atomic orbitals according to the Aufbau principle, which is lowest energy first. So we have start by filling the 1s atomic orbital, then we fill the 2s orbital, then the 2p, then the 3s, then onto the 3p, and then the 4s orbital, and another 4s orbital fills before the 3d orbitals, because as you can see here, the 4s orbital is lower energy than the 3d orbitals. Then after the 3d orbitals are full, we start filling the 4p, and then we move on to the 5s, and then the 4d, then the 5p, then the 4f, then the 5d, and finally the 5f. I'm going to give two examples of S block elements. First, we have the beryllium. You can see here the electron configuration of beryllium is 1s2, 2s2. If we go according to the off-bow principle. Then another example is the potassium, and the electron configuration of the potassium is 1s2, 2s2, 2p6, 3s2, and 3p6, 4s1. Then here's how get it according to the off-bow principle. And that's all. Thank you for watching.
So, good morning, ma'am, and good morning, classmates. Brief introduction, I am Mohammad Asnawi Dalidig, and today, to give you guys a better understanding of our report, or electron configuration, I will be in charge of discussing about the elements found on the P block and the elements found on the D block. So, as you can see here, P block elements are usually found on the right side, and as for the D block elements, they are found between the S block elements and the P block elements, or to be in short, they are usually elements found in the middle of the periodic table. So let's begin with the P block elements. As I've said earlier, P block elements are usually located on the right side. P block elements are elements that have p orbitals on the right side of the table. I will say this because there's one exception. Helium, although is located on the right side of the periodic table, does not have a p orbital. So that's something that we have to remember. Aside from that, P block elements usually have 2 electrons on their outer shells. The boron families, or the group 3A, carbon families, group 4A, nitrogen families, group 5A, oxygen families, 6A, and halogen families, or the group 7A, and as well as the noble gases, all belong to the P block elements. So moving on, those are the examples of P block elements. After that, let's talk about the D block elements. As I've said earlier, they're usually located between the S block elements and the P block elements. For D block elements, they are usually metals only. They are also called the transition elements, as they represent a transition from highly electropositive elements or metals of S block to least electropositive elements or nonmetals of P blocks. Usually, the d orbital is filled with the electronic shell n-1. The most common examples of D block elements are zinc, copper, and nickel. That's all for today.
A piece of greetings, everyone. I am Princess Rohaira Nadjah Sacar. So today I'm going to have the sample of the F block. So we have the 4 types of subshell, and that is the S, P, B, and the F. So S have 1 orbital that can hold up to 2 electrons. The P subshell has 3 orbitals that can hold up to 6 electrons. The B subshell has 5 orbitals that can hold up to 10 electrons. And lastly, the F has 7 subshells that can hold up to 13 electrons. So this block is the S subshell. This block also is the P subshell. This block is the D subshell. And lastly, this is the F subshell. Then I will introduce you to the rows. This is the first row, second row, third row, fourth row, fifth row, sixth row, seventh row, eighth row, and 10th row. But these rows start from 3 because they didn't include the hydrogen and helium. As I mentioned, I'm going to have the example of the F block. So we'll find the electron configuration of plutonium by starting from hydrogen and making our way to plutonium. So 1 is to 2, since we are in the first row, and the S represent the S subshell, and the 2 elements since we have the hydrogen and helium. 2 is to 2 since 2 represents the second row and the S represents the S subshell, and the 2 is representing the 2 elements. 2p is to 6. 2 still representing the second row, p represent the p subshell, and 6 because we have the 6 elements. So 3 is to 2. So the 3 represents the third row and the S represents the S subshell, and the 2 because we have the 2 elements. 3p is to 6, 4s to 2, 3d is to 10, 3d is to 10. This represents the third row, because they excluded the helium and the hydrogen row. 4p is to 6, 5 is to 2, 4d is to 10, 5p is to 6, 6 is to 2. So it looks like that it has an empty element, but no. It represents the F subshell. 6p is to 6, 7 is to 2, and 5f is to 6.